Yeah, over to you.
Thank you, Suraj. Thank you very much for giving an opportunity to present my work in this conference. So this is a joint work with Mahan Mj. Let me start by saying that I will restrict myself only to discrete groups. That this is because a lot of the results that I'll be saying will be true for topological groups also, but for simplicity, we will only stick to discrete groups here. So what is property T? Property T is a representation theoretic rigidity property of a group. So when we say rigidity, we mean that there is some object which cannot be deformed. So what is the object here? The object is a invariant vector in a unitary representation. And what is the deformation of such an object? A deformation of such an object is a almost invariant vector. So what do I mean by a almost invariant vector? You fixed a finite set K, subset K in G and epsilon greater than 0, and you say that a vector, unit vector is K epsilon almost invariant. If you hit it by any element of this finite set K, then it will not move by a distance, will not be moved by a distance more than epsilon. And a group is said to have property T if there exists a fixed finite set K and epsilon greater than 0, such that whenever a unitary representation of G has a K epsilon almost invariant vector, then it must have an invariant vector. And in this case, the pair K epsilon is called a Kasdan pair. Okay, so this seems like a very abstract setting, but it has many very wonderful applications. My favorite is construction of expander graphs. Also, this puts a restriction on the action of a group on a tree on a real or complex hyperbolic space, which is that they must have fixed point. And if the action on a circle is sufficiently regular, then it must factor through a finite cyclic group. Also, this rigidity property transfers to ergodic theory. For example, ergodic actions of property groups are always going to be strongly ergodic. So let me tell you some two very interesting consequences for groups having property T. The first is finite generation. In fact, Kasdan introduced property T to prove finite generation of higher rank lattices. So lattices in Lie groups, semi-simple Lie groups, they are fundamental groups of manifolds, finite volume manifolds. But if the manifold is compact, we know that it is homotopically equivalent to a finite CW complex, and therefore its fundamental group must be finitely generated. But in the finite volume case, we don't know. So we are trying to prove case by case, but Kasdan just showed that all higher like lattices will have property and therefore they will have finite generation. So if you're wondering how representation theory comes into picture while proving finite generation, let me give you the outline of the proof. So you you enumerate all the elements of G and let Gn be the subgroup generated by the first n elements. And then it is enough to prove that G mod Gm is finite for some m. And this is equivalent to saying that the L2 space of G mod Gm has non-zero constant functions. This is because non-zero constant functions are square integrable if and only if the space is finite. So what you are looking for is actually a invariant G invariant vector, because non-zero constant functions are the only invariant G invariant vectors in G mod L2 G mod Gm, because the action is transitive. And then you apply property to find an invariant vector in the direct sum of all these representations, which will imply the existence of an invariant vector in some L2 G mod Gm. And that is the proof. So the other interesting consequence is that a group having property T must have finite Abelination. This is also historically a very important result, because the Abelination of a fundamental group is the first homology group. And if that is finite, that means the first Betti number is 0. So the result that all higher rank lattices have property T means first Betti number of all higher rank logarithmic spaces must be 0. And this is in contrast to rank 1 case, where you can, given a logarithmic space of rank 1, you can always go to a finite cover so that the Betti number is non-zero. And the proof of this it goes like this. So if G has property T, then any quotient of the group must also have property T. And then there's a fact that if a group is both amenable and has property T, then it is finite. I don't want to go into definition of amenability, but let me just say that all abelian groups are amenable. So now you take N to be the commutator subgroup of G. Then G mod GG is the Abelination. So it has property T and it is abelian. So if it was infinite, it would not have property T. So it is finite. Okay. Now let me give some motivation for our question. So if two groups have property, whether also has property T, which is true. In fact, we can ask a more general question. Suppose you have a short exact sequence, and if the quotient and the kernel both has property T, then does the group itself has property T? And the answer is yes. In fact, more generally, we have this result that if there's a result that if G has property T, if and only if the quotient has property T and also the pair G comma N has property T. So what do I mean by a pair having property T? It just means that whenever whenever there's a representation of G having a almost invariant vector, then there is a N invariant vector. So instead of having a G invariant vector, now we have a N invariant vector. Okay, so let me just note that if there is a subgroup H, which is between N and G, and H has property T, then the pair G comma N also has property. This is more or less obvious. So now let us define what is fiber product of two groups. So you take two surjective group homomorphisms F1 and F2 to the same group H, and then you look at a point of H, and you look at the fiber of F1, and you look at the fiber of F2, and you take their product, and then you take union over all elements of H. Then this is the fiber product. So let me first away note that this fiber product fits into two short exact sequences. So let N1 and N2 be kernels of F1 and F2. Then you can look at the projection of the fiber product to the second coordinate, and the kernel is N1 cross 1, that gives you the first. And then you can look at the projection to the first coordinate, and the kernel is 1 plus N2, that gives you the second short exact sequence. Now let me give you some examples. First, I will take H to be the trivial group. Then the fiber product is just the product of two groups. And another example is when we take a fiber product of two copies of the same map. And in this case, note that the diagonal map from the group to the fiber product, this is a section of both the projection to the first coordinate and the projection to the second coordinate. So both of these sequences split, and therefore you can write the fiber product as a semi-direct product of G and N, where N is the kernel. Okay, now let me, to be completely clear, what the question that we are asking is that if G1 and G2 have property 2, then does the fiber product also have property T? Okay, so let me start by giving a sufficient condition. The condition is that if F1 or F2 has a section, then the fiber product will also have property T. So what is the strategy of the proof? The strategy is that I use the section of F1 to get a section of the projection to the second coordinate. And so so basically I'm embedding the group G2 inside the fiber product G1 cross G1 fiber product G2. And this embedding we will show will also contain 1 cross N2. And then 1 cross N2 is the kernel of the short exact sequence, the other short exact sequence. So because G2 has property T, and by the fact that we noted before, the fiber product comma 1 cross N2, this pair must have property T, and then G1 has property T. Therefore, the extension criteria applies, and we will have that the fiber product has property T. So how do I get a section of the second projection map starting from a section of F1? So let me draw a picture. Let me represent H by this line, dotted line, and then we represent the points of H by these dots, and let these lines be the fiber of the second map F2, and these be the fibers of the map F1. And then we have sections of F1. So these are denoted by these points in the fiber. And I want to embed G2 in this fiber product. So what I do is at every point, I take the section element as the first coordinate and the elements of and the fiber of G2 and in the second coordinate. So we will kind of get these parallel lines through the section elements, and that will give me an embedding of G2 in the fiber product. And note that the image of if you want to write it in algebraically, then this is the expression, and the note that the image of N2 is 1 cross N2, and therefore this is inside the image of G. Okay, so now I will give you some counterexamples. So as I said, that if a property group must be finitely generated. So the question is, if I have two finitely generated groups, then will their fiber product also be finitely generated always? And the answer is no. So we prove that if G1 and G2 are finitely presented, whereas H is not finitely presented, then the fiber product will not be finitely generated. So how do I use this to get counterexamples? So there's a theorem of Shallow, which says that even if my property group is not finitely presented, I can always write it as a quotient of a property group which is finitely presented. So all we need to do is to find a non-finitely presented property group and then call it H, and then Shallow's theorem will give me G1 and G2. So what are examples of property groups which are not finitely presented? Many people give these examples. For example, Margulis, Gromov, Cornelier. I don't want to go to details of this. So let me make some comments on the proof of this theorem. So we use the very simple observation that if N is normally finitely generated subgroup of a finitely presented group G, then the quotient N mod G is also finitely presented. So what we do is we go prove it by contradiction. So we first assume that the product is finitely generated. Then the finite presentation of G2 implies that N1 is normally finitely generated in G1. And then we'll apply the observation on G1 N1, which will imply that H is finitely presented. And this is a contradiction. The first step requires quite a bit of work, but yeah, it can be done. Okay, now I will give you some examples which will contradict the finite Abelination of property groups. So suppose you take a homomorphism whose kernel is contained in the center and is infinite. Then the fiber product of two copies of this map will not have property T. So as we said before, a fiber product of two copies of the same map can be written as a semi-direct product. But in this case, the normal subgroup is inside the center. So the G action on it by conjugation is trivial. So the semi-direct product is in fact a product. So N is in fact a quotient of the higher product, and it is abelian and is infinite. So that means that it does not have property T, and therefore the fiber product itself does not have property. And there are examples of such homomorphisms also. Again, I don't want to go into the details. Now let us give an example in the world of hyperbolic groups. So there are a lot of hyperbolic groups which have property T. So we will again use the special case of fiber products of two copies of the same map. And in this case, we know that it can be written as a semi-direct product. And so what is the Abelination of this semi-direct product? The Abelination is the Abelination of G product N mod the commutator subgroup of G and N. So if N mod Gn is infinite, then it will contradict the finite Abelination property, and therefore the fiber product will not have property. So if we have a good handle on the action of G on N, then it may be possible to compute N mod Gn. So, and in fact, if you look at hyperbolically embedded subgroups, then they satisfy a property which is called the Cohen-Linden property, which will give us this good understanding of action of G on a normal subgroup. So what does Cohen-Linden property mean? So suppose you start with a subgroup H of G and you take a normal subgroup N in H. And then you take the normal closure of N in the whole group. And note that if you take any conjugation of N by an element of G, then it is inside the normal closure, obviously. So you can take a free product of all these conjugates of N, and that will map to the normal closure. But there are like there are many redundancies here, in the sense that you can take a free product of conjugates over a much smaller subset, so that this map from the free product to normal closure of N is still surjective. In fact, if you take a set of left process representatives of H into the normal closure of the group H into the normal closure, and take the free product over only this set, even then the map to the normal closure will be surjective. And what Cohen property says is that the map will also be injective. So that is, N can be written as a free product of the subgroups T and T inverse, where T varies over some left positive representatives of Hn in H normal closure of N in G. Now, what happens if we have this property? Then we will have the normal closure of N modulo the commutator subgroup of G comma N is N modulo H comma N, because this is, if you want to go formally, it's a bit of work, but notice that when I'm going modulo the action of G on normal closure of N, that means that this T and T inverse, these things will start commuting. So T and T inverse will cancel, and only N will be remaining, and then you have to quotient by action of H, which is kind of the normalizer of N. Okay, so now there is a theorem by Sun. He is a speaker in this conference, in fact. He proved very recently that if H is a hyperbolically embedded subgroup of G, then the pair GHN has Cohen-Linder property for all sufficiently deep normal subgroups. So by sufficiently deep, I mean it has to avoid a fixed finite set of elements in H. So all we need to do is to find hyperbolically embedded groups such that N mod, such that we can find normal subgroups there, such that N mod Hn is infinite. So so you can take H to be infinite abelian, and then obviously this is for all finite index subgroup. But you can also take the free H to be the free group of rank more than 1, or a surface group of genus greater than 1. In these two cases also, you can use the Chevalier-Well theory to prove that N mod Hn is H comma N is infinite. And so in all these cases, if you look at the two copies of the quotient map G to G modulo the normal closure of N, then the fiber product of that does not have property. Okay. Now I will come to some equivalent conditions in the special case of fiber product of two copies of the same group. So as I said, it is the semi-direct product of G and N. And then we can ask a slightly more general question that if suppose you have abstractly you are given a group G and it acts on a group N by automorphisms, and G has property T, and then the question is, when does the semi-direct product have property T? And the idea is that since G already has property T, then it should be possible to check whether the semi-direct product has property T purely in terms of unitary representations of N and the G action on N. Okay. So I define property T as a property of all unitary representations of G, but property can be also expressed as a property of, I can look at a finite subcollection of all unitary representations, and property can be expressed in terms of that. This subcollection is a subcollection of cyclic representations. So what is a cyclic representation? A representation is called cyclic if there exists a vector such that you look at the image of this vector under the G action, take its span, take its closure, and it will give you the whole space. And in this case, the vector V is called a cyclic vector. So if you are given a cyclic representation, then you can associate a function to it, a function on G, which is given by G going to the inner product of pi GV comma V. And these such functions can be characterized abstractly. And in fact, by abstractly, I mean without reference to any representation. And these are called functions of positive type. And then there is a GNS correspondence which says that given a function of positive type, you can in fact construct a cyclic representation from which this function of positive type is coming, and this uniquely determines the cyclic representation up to isomorphism. So instead of looking at the space of cyclic representations, I can look at only the space of functions of positive types. And here the property T can be characterized by this result. It says that if you take any sequence in normalized functions of positive type, normalized means it should take one at the identity, then, and if it converges uniformly on complex subset to the constant function 1, then it has to converge uniformly on all of G. So what we did is we give a version of this theorem in our context, where so we took a group G, and the action of G on N induces the action of G on the space of functions of positive type. And then we say that the symmetric product has property T if and only if every sequence in G fixed points of functions of positive type of N, if that sequence converges uniformly on complex subsets to the constant function 1, then it has to converge uniformly on N. Note that if we take G equal to 1, then we get back the previous result. Okay, so now property T can also be expressed in terms of affine isometric actions. So a group is said to have property T if every affine isometric action on a real Hilbert space has a fixed point. This is also called property FH, and you can show that these two definitions are equivalent. And in this case also, we can define what is the cyclic affine action, and then we can define corresponding to each cyclic affine action, we can define what are called functions conditionally of negative type. And then there is a GNS construction similar to what we had before, which says that all cyclic affine isometric actions up to isomorphism are in one-to-one correspondence with functions conditionally of negative type, normalized. And then we have a characterization of property T in terms of functions of conditionally negative type, which says that a group has property T if and only if all functions conditionally of negative type on G are bounded. And in our context, this becomes that if the semi-immediate product has property T, given that G has property T, if and only if every G invariant function on a G invariant function of conditionally of negative type on G is bounded. And again, we note that if we take G to be a trivial element, trivial group, then we get back the previous result. Now, also there is a GNS-like construction if we are looking at n abelian, and in this case, spectral theorem lets us associate to every cyclic representation of n a regular probability measure on the unitary dual of n. Unitary dual means you look at all the equivalence class of irreducible representations on n. So then we have the GNS construction, which says that cyclic representations are determined up to isomorphism by regular probability measures on n hat. And then we have a characterization of the existence of of property of semi-immediate product when n is abelian. So let the delta 1 be the Dirac measure at the trivial representation in M of n hat in the n hat. Then the semi-immediate product has property T. Always we are assuming that G has property T. So the semi-immediate product has property T if and only if if you take a sequence in the G invariant probability measures, which converges to the Dirac measure, which does not have any atom on one, then there cannot exist such a sequence. So that is another characterization of property for semi-direct products. So that finishes my talk. Thank you very much for your attention.
Let's thank the speaker. Any questions for Arghya?
Hi, I have a query.
Yeah.
Yeah, so can we talk about this property P for other different type of products, as in free products or amalgamated products? And if so, is there anything done for them?
Yeah, I guess. No, I don't know about amalgamated product, but for free product, I think. So for free product, any rotated representation of a free product is already determined by the restriction at every free factor. So I am guessing in this case, it should not be hard to say that, but I am not aware of the result. But I think it is true in this case. But for the other one that you said, amalgamated free product, I don't know.
So, but for free products, there is an action on a tree without a fixed point.
Free product of property T groups?
Yeah, of any two groups, yes.
Okay. Then probably it's not true.
So I think maybe even for amalgamated products, it must be the same. So because there is the Bassett tree. And, yeah.
Okay, thank you.
Any other questions? So I have a question, I think, about this hyperbolically embedded subgroups thing you mentioned.
Yes, let me, yeah. Go ahead.
So is it required for, is it required that G has to be hyperbolic in this, or?
No, so those are, I mean, I said hyperbolic because there are many examples of hyperbolically embedded subgroups of a hyperbolic group.
Okay.
So yeah, quasi-convex normal subgroups and stuff like that. So that's why and also hyperbolic groups, many hyperbolic groups are known to have property. That's why I mentioned.
Okay. But for this theorem, you
don't
need.
Yeah.
Okay. Thanks. Okay, let's thank the speaker again.